All right. Mic is working. Yes, can people online hear me?
Hi, people online. Can anyone hear us? Yay!
Okay,
Yeah.
great. Cool. Wanted to make sure, otherwise the recording is just going to be like silence for the first half, and we don't want a repeat of that. Welcome to discussion 5. Today we're talking about cryptographic hashes and Mac. So again, yeah, I know this was like 2 weeks ago or like a week ago, but because we are trying to discussion, it's a little bit weird. Before we dive into things, questions on what lecture material, content in general, logistical questions about the exam or anything else? Okay, why don't we get into it then? So we've spent a lot of time talking about encryption. So this protects our data. It means that no one can read it. But today's discussion, we're going to be talking about how do we ensure integrity and authenticity over our data. So remember, in cryptography, we not only want to make sure that the adversary can't read our data, we also want to make sure they can't tamper with our data. So if I send Ron, you need to work 10 hours today, Ron, or not today, but this week, someone can't modify that message and Ron thinks, oh, Nicholas is asking me to work 100 hours or something.
Oh, geez, yeah.
Yeah, please don't do that. That's illegal. So getting into our primitives, before we talk about how we protect messages with like a key, we first talked about hashes. So these are cryptographic hash functions. You can think of them as a fingerprint over some message. So if I have some like gigabyte long file, if I hash that, I'm just going to get a fixed length string, and that's going to represent the original file. You might think, okay, well, if I have a gigabyte of data and like 256 bits of output, that doesn't seem like it could possibly represent every single message. And you're kind of right there. So let me go into a couple of the properties that we have with Mac. So the first one is that hashes are deterministic. If I hash something, and then later I hash that something again, I want to get the same output out. Going back to the fingerprint analogy, my fingerprints don't change every day. I guess they kind of do, but they don't really change for the purposes of this analogy. So in the same way, if I hash something and then I hash it again, I want to get the same output out. We also say that hashes have this property called one-wayness / pre-image resistance would be the technical term. The idea here is if I have a hash, I can't get back to the original message. And it's actually a little bit more firm than that. If it says that if I have a hash output, I can't find any input that hashes to that. And we'll sort of, after we go through the first question, hopefully you'll have a better intuition of how it works. That's the first one. The second one, and finally the third one is collision resistance. So this is kind of the, I'm not going to say it's the most important, but it's the most interesting to think about when it comes to hash functions. What it says that for the hash function in total or in general, I cannot find two inputs that ever have the same hash. So if I can't find, let's say, h of x and h of y that have the same hash. That's an equal sign. It's just going the wrong way. I don't know why I wrote it like that. And it's a little bit weird because if we think about the possible inputs for a hash, by writing it out mathematically, this little star symbol here, we're doing all possible bit strings. So anywhere from like 1-bit inputs to basically infinitely sized inputs. And we're trying to turn this into a hash of some fixed length. Let's say it's 256. Now, there are a lot more inputs than there are outputs. So if you took 70, you might remember this thing called the pigeonhole principle. There must be inputs out there that have the same hash. And the guarantee of hash functions is that it's just really hard to find them. It's approximately as hard as someone guessing my secret key correctly. So for the purposes of, I guess, reasoning about security guarantees, you can't find these collisions. They exist, but they don't exist because they're not. You can't find them. Questions on that? All right. So some algorithms that you might come across in your day-to-day life. You've got MD5 and SHA-1. Those are crossed out because those have been broken. So you should never use these unless you're using Git, because Git uses SHA-1, but we won't talk about that right now. And then the modern ones that you should use if you ever made a hash function are SHA-2 and SHA-3. SHA-3 sounds like it's more advanced. It's not really. It was basically designed because they didn't want to put all their eggs in one basket. Because if someone broke SHA-2, then we wouldn't have a hash function anymore. So now we have like two. If we lose SHA-2, then we have SHA-3. If we lose SHA-3, then we have SHA-2. All right. Yes.
What exactly does it mean for SHA-1 to be broken like 100%?
People have found collisions on SHA-1. So if you go to, I think it's shattered.io, shattered.io, you'll see like someone has two files, and if you hash them, they have the same output, but the files are different. So someone has found a collision, that means collision resistance.
So one single collision.
I believe, well, so when they published it, I think it was one, but I think they also published like these are the weaknesses which allowed us to find it, because they couldn't brute force it, that would still be too much work. But they found weaknesses and that allowed them to create a collision, which is bad.
That was in 2017.
Yeah, that was a while ago. I think I was in a study hall somewhere when I heard about that. All right, so that's hash functions in a nutshell. Why don't we, I had a discussion sheet slide in there, but it's not there anymore. Why don't we go through question one? This one's fairly simple. It's basically just giving you a couple of different possibilities for hash functions, quote unquote. And your job is to analyze the properties that they have. So either they're one way, or they're collision resistant, or they're both, or they're neither. Make sense? Cool. Okay, we'll spend, this one isn't too long and it's only 3 questions. Why don't we spend 4 minutes on this? And then we'll come back and discuss answers. And in the meantime, if you have any questions, feel free to ask them. Yes. Oh, did we not specify that on the sheet? Yes, SHA-256. So I mentioned SHA-2. SHA-2 is actually like a family of functions, and SHA-256 is one of the SHA-2s. Yeah, sorry. Good question. Probably something we should clarify. A note of that.
We're not using the restrictions. This one is just
Okay. How are people doing on time? If you still need time, raise a number of fingers equal to the number of minutes you think you'll need.
If you're on the chat, feel free to
Yeah.
say or type how long you need.
All right, here's our first hash function. I know hashes are usually on bit strings, but just pretend they also work in numbers. What do you think? Is this one way? No, is this collision resistant?
No.
All right. So first of all, let's talk about one-wayness. Let's say I give you the hash value 9. Can you find me a possible input that hashes to 9? Right. How did you do that? Right. You'll notice that if, say, h of y equals 9, this is really just y squared equals 9, and we can actually just algebra our way through it. Y is equal to plus or minus 3. And it actually doesn't matter whether I originally hashed positive 3 or minus 3. Remember that one-wayness just says I can't find any input that hashes to the given value. Okay, very good. Number 2, hash of x equals SHA-256, which is a secure hash function for now, from 0 to length of x minus 1. So this notation is a little bit crazy, but basically we're hashing everything except the last bit of the message. Did you have a?
Why is the first one collision resistance? Because -1 and 1 will go the same thing, and -2 and 2 will go the same.
-1, first one is not collision resistant. So this is
neither, right?
they're neither, yeah.
Okay.
This is neither.
Okay.
Who thinks this is one way? All right, who thinks this is collision resistant? Okay, let's talk about one-wayness first. So anyone want to explain why they think it's one way?
Because SHA-256 itself is one way. You
Mhm.
cannot come up with any sort of input for that segment. Just because SHA-256 itself is.
Yeah, so that's a good way to build the intuition. If you wanted to prove it formally, you could say, let's assume that this is not, let's assume this is not one way. Thus, I must have found something that hashes to this inside. And thus I have broken the one-wayness of SHA-256. But I can't do that, so the function must be one way. Kind of a proof by reduction if you did the CSMD. All right, so this is one way. Let's go OW. I don't know if there's a better abbreviation for that. How about collision resistance? I see some shaking of heads. Does someone want to propose a collision you can find?
It's not collision resistant because like the last bit is not being hashed, right?
Right.
So let's say you have 2 bit strings,
Mhm.
but like the first like x minus 1 is the same, but the last one is a 0. And the second one is, last one is a 1 instead. Those 2 bit strings map to the same hash.
Right, so let's say I'm hashing 10111. What's something that would collide?
0.
Right, 10110. If we look at this, the hash of this, hash of M1 is going to be SHA-256 of 1011, because we're turning off this last bit here. And the hash of M2 is going to be SHA-256 of 1011. We have the same inputs, hashes are deterministic, so these have the same hashes, even though the messages are different. So this is one way, but this is not collision resistant. Very good. All right, third one. Oh, okay, second. Go ahead.
Every 0 index to the length -1 should be the whole thing. Like it starts 0, 1, 2, 3, 4, and the length is 5 minus 4, and then goes 0 to 4. So you get the whole thing.
Sorry, say that one more time.
Sorry, isn't the length of the whole thing -1? Wouldn't that just be the whole thing?
It's exclusive.
Yeah, we're doing a half exclusive range here. You're right that usually in math, we actually do inclusive on both sides, whereas in something like Python, we don't. But yeah, for the purposes of this question, and it says right there in the question description that this just says half inclusive because it's x to y minus 1. All right. Good question. All right, third question. We have hash of x is equal to x cubed. Who thinks that this is one way? A shaking of the head and a hand raise. All right. I guess, do you want to explain why? Okay, hold on. Who thinks it's one way? Who thinks it's not one way? Who thinks it would be one way if we only allowed real numbers? Or, wait, sorry, I'm thinking of the other one. Sorry, okay. So let's say I have, sorry, I was thinking of imaginary numbers for a moment. I'm not sure why my brain went there. All right, let's say I have some hash of x is, I don't know, 8, sure. You're one step ahead of me. What's the, how would you reverse this? Right, cube root. So it's the same kind of problem as up here. In this case, again, if you're only constraining yourself to real numbers, the only input that would hash to this is 2, right? Yeah. But because we reversed it, we broke in one way. All right. Who thinks that this is collision resistant? All right, why?
The problem that x squared has.
Right. Yeah, probably looks like that, but oh, that was horrible. Say that again. X cubed looks like this. You can kind of see by inspection that it's one way, because there are no, you know, this isn't really a valid hash function because the length is not fixed, but you kind of get the idea. So, yeah. Yes.
Like need to consider complex values and this.
No, I was confused because my mouth was saying one way and my brain was thinking collision resistant. So I was like, why is everyone saying it's like not collision resistant? But then I understood what was happening. So you don't need to worry about imaginary numbers. Usually hashes deal with bit strings, but for the purposes of this question, we just needed something to do with numbers. Yeah, sorry about that. That was entirely my fault. All right, any other questions before we move on to math? Okay, if not, then let's see if I can get, I don't know. Okay, there we go. All right, so maths are kind of similar and at the same time very different. You can kind of think of them like a hash function, except now it takes a key. So something like HMAP is actually a valid function, is actually a valid hash function, HMAC. And if you fix the key, then it's actually a valid hash function. But in general, maps do not have to be hash functions. So there are 3 main elements to the system. We need a way to generate a key. So this is kind of consistent from scheme to scheme. We need some kind of key generation. We have a function that generates a map. So this function, once we have a key, it generates a tag for the message M. And the idea is you can only generate that tag if you have the key K. And I lied because I was thinking about a different kind of max scheme. There are actually only 2 schemes here. Anyone want to tell me really quickly how we verify a map? Say you receive some message M and some tag, how would you verify it? Yes.
You map it yourself.
Yeah. So let's say, oh, I received from Alice, I got M and I got T. And I want to check, is the map under, say we share key K of the message I received, are these equal? If they're equal, then I know that malware has to change the message, otherwise the map would be different. Yes.
What if you, so like this is assuming you have the message you're hashing first, right?
Yes.
Okay.
So remember, tags are fixed length, so you need to send the message along with the tag. Yeah. You can't recover the message from the tag.
Wait, but I thought the whole point was like, you like you'll get a message. And then just like to assure that like, it's like the right thing, you check if your tags, your tag is the same as the tag that the other person. Oh, yes.
Yeah.
Okay.
Yeah, so I mean, I think in both what I was describing, you were describing, you need to have the message on hand. So presumably they've sent you a tag and they've also sent you the message. Yeah.
Oh, sorry. Surely, like if someone was like trying to corrupt the message then, right? Why wouldn't they just like corrupt the tag too?
They would.
So if they corrupted the tag, well, the guarantee of maps is that even if they corrupt the tag, they can't generate a valid tag for any message.
Oh, because they don't.
So the worst they could do is just cause verification to fail. And, you know, it's a valid attack. If I don't want to Alice and Bob to communicate, I can just, you know, corrupt their communications.
Sure.
But I can't trick Bob into thinking Alice sent a message that she didn't.
Okay. that
Yeah,
makes
and that's kind of the guarantee of integrity.
sense. Okay.
Another question? Oh, okay, cool. So some properties that we need from this, we need to it also needs to be deterministic. So if we have the same key and the same message, then we'll get the same tag out. And again, this is because we need to be able to verify the maps by computing it ourselves and seeing if the tags match. Our security definition for this is the CPA. This is an acronym or an initialism for existentially unforgeable under chosen plain text attack. I'll show you what that looks like very shortly. And some algorithms that you'll see here are the one we learned in class is HMAP. There's another one that one of the other professors likes to teach called AES-EMAP. It's actually built on the CBC mode of encryption, but it's out of scope for this semester. So this security definition, it's a lot simpler than in CPA, despite the similarities in name. You see, again, we have this challenger who has some secret key, and we have an adversary. And really, the only thing the adversary is doing is, here's a message, I'll get back its map. Here's a message, I'll get back its map. And eventually, it's going to try to form a new message and a new tag that would be valid, but that the challenger didn't generate. Because otherwise I could just ask for any message and then output that. That's not really that interesting. So we add the extra requirement that the adversary has to forge a new tag for a new message that hasn't been requested. And I think unlike in CPA, this game is fairly intuitive because it's literally if the adversary can generate a fake tag or a valid tag for a message or for a message without the key, then they've broken the integrity. So this one's fairly intuitive. Are there any questions on the security definition? Or about maps in general? Okay, cool. So that's kind of all you need to know to do this second question. This one, I think some background will actually be interesting. This is a boiled down version of an exam question that was given during summer 2020. So this is actually fairly close. This pretty much is exam level. So if you kind of wanted some review on that, now you have it. Why don't we spend 10 minutes working on this, which is not a lot of time, I know, but it's I am hoping to get through this entire sheet today. And then we can come back and talk about it. And again, feel free to ask questions if you have any in the meantime. Yes.
The two bars, are they like sorting or?
So double bars, I guess this is something we should probably clarify in lecture at some point, but double bars is always going to mean concatenation.
Oh.
Mhm. Yeah, it's like the plus operator on strings in Python. Yes.
We assume that like the hash is not, that it is one way, it's not. And supposed to be this one?
Yes, you can assume this is a secure hash. Yeah, I guess we say map is a secure map, and we just say H is a cryptographic hash.
Yeah.
It's a secure hash, yeah.
assume Mallory can know the algorithm and hash function, right?
Yes, you should always, so that's Cracker's principle. You should always, assume the adversary knows everything except the key. When did it fire erase this first question? Good. Ow.
So is Mallory unable to run the Mac function?
Yeah, well, we'd say she's able to run the map function, but she doesn't have a key.
Oh.
Mhm.
Hash has to produce something that's of like the same length every time.
Yes, a hash, by definition, it produces a fixed length output.
Does Mac have that property?
Yes.
Yeah.
Yes.
So in this problem, is Mallory only able to change first name and last name? She can't do anything with the functions.
She can't change the functions because those are going to be just computed
So
by
so
whoever's
only
trying
she
to.
could modify his first name and last name.
Yeah, first name, last name, and the cryptographic
Once you just
log
change
sorting
the
method.
tag that you produce, I think you change the note input, the first name and last name. And it's
Well, so I
modified
guess in this model, what we're saying is there's some table out there, like on some server somewhere that has a first name, has a last name, and it has, some cryptographic stuff. So maybe we have like Bob, Joe, I don't know, maybe that's Bob Joe, let's go with that name. And then in the first case, we're saying oh, they're just storing the hash of these two fields. The second case, they're saying, oh, they're concatenating them and storing the map here. And so we're saying for each scheme, can Mallory change the value to literally anything she wants?
And it still becomes a valid.
Yeah, so, and verification would succeed. Or can she?
So what is Mallory changing? The result of running the function?
First
So
and
that
last
was-
name.
You can
I guess-
change any of it as long as it looks valid.
Yeah, if
Except
it
for-
change Bob and Job, but like if the tag still matches.
Yeah,
then it means you.
so Mallory wants to modify this record to something else while still passing verification.
So does the order matter for the match? Like Bob, Joe, and Joe, Bob will all go with different tags?
So Bob Joe and Joe Bob are two different names.
Yeah,
So if she can switch them, that would be a violation of integrity. Or that would be a record that she could generate.
so like it has access to hash functions, can we write? Yeah. so then it is valid and the other- you know, like everything. Or you can choose another thing. And then, that's what I.
All right, in the interest of time, why don't we walk through this? So this first question, we're storing a hash of the first name concatenated with the last name. Raise your hand if you think it's A. She can choose any value. If you think it's B, she can only do some other value. C, she can't tamper with this at all. All right. Yes.
No, just.
Oh, okay.
Yeah, that's fine.
So it seems like most of us said she can choose any value she wants. So let's say we want the first name. Let's say we want the first name to be A and the last name to be B. How would she generate a valid thing to go in this field here? Yes.
Just hash AB.
Yeah. Hash is a public function. She can just generate the hash of AB. And this is a valid, this would verify. Questions on this? Yes.
But then, so like, are we saying now Mallory just has like access to AB? Like, I'm confused, like, kind of the question, because like, in this case, like, Mallory didn't like modify anything, she just knows what the hash of AB is.
Sure. Well, so what's being stored in the database here? In this case, it would be the hash of Bob Joe. What she can do is now she's like wiping out this field, or maybe she's just adding another row. That would be A, B, hash, A, B, and this would be a valid record.
Yeah,
So now when Bob or whoever owns this database comes along, he sees, oh, I have a record that has first name A, last name B. Let me check that it verifies. Oh, it verifies correctly. And now we've tricked Bob into thinking, but now we've tricked Bob into accepting one of our tempered records.
oh, I see, so it's just modifying the record of the whole, not like going in, like changing Bob to like Box or something like that.
Yeah, well, we could do that if we had, say, boss Joe. What would the way of tricking Bob into accepting this be? What would we put here?
Hash, Bob Joe.
Bob Joe?
Boss Joe.
But I'm
Boss
saying
Joe.
like if we, I was just saying like Mallory can in this case, like go and then change Bob Joe to like Boss Joe.
You can.
Well, like, you
Well,
can
she just
change
did.
Bob Joe to Boss Joe and change the hash function accordingly, because you can modify everything on the table. Bob doesn't know anything about the table, he just receives it and checks whether or not the inputs are valid.
Or yeah, so but like in this case, like now we have like Boss Joe and Bob Joe now.
Like, just delete one row.
Yeah, Or I guess,
I guess you can just change it, right?
yeah,
Like, how would you change it? Because like, if we put in like, right, like, we can't change Bob Joe right now.
Why not?
We
Why
could.
not?
That's the,
Like, how?
That's
Good
a-
call.
just-
Hash
We're allowed
function
to.
there is not just, it is not unchangeable. If you change Bob Joe to be Boss Joe and change the hash function, like the hash function there to be Boss Joe's hash,
It's still valid.
it's still
yeah.
valid.
So recall that Mallory is an active attacker, right?
Yeah,
So she can tamper with any of this data in this table. So if she tampers with Bob to turn into boss, leaves Joe alone, and she tampers with this to turn it into the hash of boss Joe, this still looks like a valid record to the owner of the database.
but then in that case, right, she would have to know like some hash that both correlates with Boss Joe and Bob Joe, right? Those two inputs both have to output the same hash, right?
Not quite, she can just change this hash.
Like
Yeah,
the
definitely the
hash
same.
function itself.
Well, she
The
knows the
output
hash
of the
function.
hash function. So the table has three things: name, surname, and the hash function. The hash output. So you can go and modify the last column.
Yeah, so the algorithm, if you want to think about it this way, that the database is running is for each row, concatenate the names and see if it matches what's stored in this field here.
Sure, yeah.
So now when we get to this row, it sees first name is Boss, last name is Joe. Concatenate it, does it hash it, does it match what's in this field?
Mhm.
And it does match. So it would be, so this would pass that verification.
Yeah, that makes sense. But like, let's say the table is already in place, like, I'm confused, how would you tamper with things that are already there? Because like, in that case, like, if you just add extra things to a table, that's like not necessarily tampering with like the older information.
Well, you can just change the information. Tampering just means you can change it to anything you want, right? So you can change existing records as well. We're just saying, can Mallory trick the database into accepting a record or into validating a record that wasn't actually there? Yeah,
Okay.
let's chat about this more offline, because I think there might just be some weird wording issues with this question. Cool, I don't, yeah. For the second question, now we're introducing a map. We're taking the first name, concatenating with the last name, and mapping it with the key K. So who thinks that Mallory can choose any value that she wants? Who thinks that she can modify it to some other value, but not one that she chooses? All right, and who thinks that she just can't tamper with this? All right. People who said, we're counted 2-2 here, so we'll just go with the first one. If you can, let's just go with this Bob Joe example again. What's another record that would pass validation?
Bo and then last name Joe.
Yeah, so we're kind of saying, oh, come on. I'm having a bad day with my markers. Okay, well, let's try here. Nope, that's not gonna work. All right, I guess, oh, wait. Aha. Okay, perfect. Now I forgot what I was writing. Yeah, that was a quotation mark. So you're saying Bo, Joe. Ignoring the fact that this is, okay, I don't want to say that, maybe some people have that last name. When you concatenate this, you just get the same thing, right? Bob, Joe. So this is going to be, all right, this is going to be the same input into the map function, and thus we're going to get the same output. So we can actually reuse this tag, and Bo Joe and Bob Joe are going to have the same map. So just because we've thrown a map in it doesn't mean that we necessarily have full integrity. Questions on this? Make sense? Cool, okay. We're all dead, sorry. Third question, we're doing the same thing, but now we have a dash in the middle. And maybe something to keep in mind is that dashes aren't valid characters. You're not allowed to have dashes in names for the purposes of this question. So who thinks that Mallory can modify it to be any record that she wants? Who thinks that she could change it to some other value, just not one that she chooses? And who thinks that she can't tamper with this? All right, ooh, unanimous. Anyone flash?
I mean, the problem with the last one is that we could move the letters
Mhm,
around, and now
mhm.
since there's a dash, we can't do that.
Mhm.
So I just don't know if really what to cool this.
Yeah, so the intuition here is we can't break the map function, so we have to find something that has the same input to the map function. But the only input that to the map function that would, or the only first and last name that would cause this input to the map function has to be Bob and Joe. Because you can't tamper with these records because we have this unambiguous delimiter here. Make sense? All right, next one. Now we're composing these schemes together here. Who thinks it's A, like it's G? Who thinks it's some value, just not one that she chooses? Who thinks it's tamper proof? All right. Why? For the third one, it seems like that was
We
ours.
assume hash function is like secure, right? No, it doesn't. Like,
Yes,
one
you can
way,
assume the
one
map.
versus
Yeah, you can assume these are secure map functions and secure hash functions.
So to change it, you would need to find like some sort of collision to hash function to actually like do the same attack as two, right?
Yeah, exactly. So let's say our input is like A46. So that's for the first name, and then let's say pincat 710F. I don't know. And so let's say this is the hash of the first name and the hash of the last name. Again, either we have to find something that's the same input into the map function, or find different names that hash with these same values. But both of these are going to be impossible because for the first one, these are fixed length strings, right? So it's not like we can just move one of these hash outputs over here, because then, because it's a different length, that's never going to be a valid output of the hash function. And we can't find collisions over the hash function because it's a secure hash function. Yes.
If it wasn't collision resistant, would they be able to modify a record but not their choosing?
Yes, exactly. Well, it depends on how uncollision resistant you. If it were like h of x equals 1, then you probably have a problem. But yeah, so if it were not collision resistant, then Mallory could probably do some of the value. You just have to find something that collides with the first name and the last name. Great. Okay. Last scheme, we're mapping the first name on its own, mapping the last name on its own, and concatenating them together. She thinks that she can change it to anything she wants. She thinks it has to be a specific value, or she can change it to some other value. Got a hand raised from online.
Can you repeat the first reason, the fixed length thing?
Oh, fixed length thing, sorry, okay. So in this attack over here, basically what we did is we moved one of the letters from the first name to the last name, right? I'm saying right, but I also don't know if you're.
Yeah, we got a yeah.
Okay, great. We can't do that in this case because we would need something where when we hash it, we get basically nothing we hash is going to have, in this case, our hash output is 4 bytes. We're never gonna get a hash output that's 3 bytes because a hash function by definition produces a fixed length output. Does that make sense? And same thing with this over here, it's 5 bytes long. So we're never going to find something that hashes to something that's 5 bytes because the hash by definition outputs 4 bytes.
Oh,
Any other?
yeah, makes sense.
chat? Okay, great.
Thank you.
All right, good question. Okay, this last one, any record ever choosing? Some other record not necessarily ever choosing. I got a maybe, all right. What about a cannot modify the record? All right. How about this? If I proposed, I gave you the map of Bob and the map of Joe, and I told you the first name is Bob and the last name is Joe. What could you do here? Right, because we have this map value. We have this map value. If we just did, I'm going to leave out the key tag. That takes too long to write. just do map of Joe. And the map, I actually change my mind, I'll put the key back in, of Bob. Okay. We have this, we can just move that over there, move that over there, swap the first and the last name here, and now we've generated something that would still pass out validation. Okay. Uh-huh.
But then like, the like output of the max would be different, so how are you allowed to just like change it?
The output of the map would be different. Well, would they? So let's say we have Bob Joe here, and we have Joe Bob here. What we're gonna do is take the first name and map it, right?
Yeah.
Well, this input is the same as when Joe was the last name and we mapped it. This input is the same as this input.
Oh, I see what you're saying.
So the last name map and this first name map are the same and vice versa. So that's why we can just swap. So, yes.
Is
question?
there a problem about key reuse here?
Sorry,
I
let's-
mean, you only has one key here, so
Sorry.
probably not.
Sorry, give me a moment. So let's dial it down a bit so I can hear. Sorry, say again.
Is there any issue about key reuse? Like if they reuse the same key, can it lose information?
Depends. So if, let's say, we didn't have the same key here, we used, let's say, KF for the first name, KL for the last name, then this would be secure, because you can't just swap them, because these are like tied to their location. It's the same thing as,
One and meaning that like K1 is always used for first name. And
Yeah.
K2 is always used for last.
yeah, I have, it's really small, but it's like KF and KL, because first name and last name. But yeah, so that's a very good observation. If we did that, we could also kind of did what we do here. If we said the first name always has to be like F and then the name, and then the last name always has to be L and then the name, then we couldn't just swap them.
By the way, even in that case, can we just like, if we have like, for example, two columns, we have like A, B and Bob Joe. Can't they just get A Joe and Bob B? And then I like, you know.
Oh, you're
So
exactly,
I can like switch in between two
yes,
lines.
you're
and
right.
get a valid-
Actually, I didn't think, okay, yeah, I was thinking about a single record, but yes, you're exactly right. If they were, I could create Bob B and that would still be valid even if I had
Have
the key
different
here. So actually, yeah, you're right. That was totally my mistake. Even if you had different keys here, that would not be secure.
Well, but I guess we had some other algorithms that would like leak information about the key you reuse.
Yeah, so now we're getting into like really complicated stuff here. If we had the row number here,
Yeah, use that.
let's say this has to be 1, 2, 3, 4. Then in that case, I think it would be secure. Because you're stuck with that row.
If we're using the same key and that leaks information, then none of our things are secure so far. If they're all using the same key.
I think if you had the row numbers.
Yeah.
And you, well, okay, actually, yeah, so if you have the row numbers, but you're still using the same key, then you can still swap them. But if you have the row numbers and you're using different keys or you're adding like F and L.
So
or 1
row
and 2.
number is also included in the math somehow?
Yeah, so if we included the map, so now we're just kind of like thinking about how we would design this.
Okay.
But yes, all very good observations. I really love this conversation. Really quickly, how many of these schemes have confidentiality? Hold up your hand. 0, 1, 2, 3, 4, 5. Yep. Zeros and twos. Remember, maps are deterministic, right? So is that going to be confidential? Confidentiality is in CPA.
Yeah,
So deterministic schemes can't be in CPA, right?
yeah.
And are the schemes deterministic?
None of the schemes are.
Right, exactly. So none of these have confidentiality.
Max are integrity.
Cool. Yeah, maps and signatures are for integrity. Encryption,
Yeah.
public or symmetric
Those
are for
non-type
confidentiality.
stuff, those were the ones.
Yeah. So we didn't get to this last question. I would definitely recommend reviewing it at some point because it talks about how we put schemes together to have both confidentiality and integrity. But you can work on it in your own time, and of course, there are solutions online. Yeah. If there are any final questions, feel free to come up and ask them. I think the other class is coming in, so let's try not to. Oh, no, that's just, never mind, that's just something. I do want to get to online people first because we have the nice conference feature. So is there anyone?
There's a thank you,
You're
and
welcome.
everyone's leaving.
Everyone's left. All right. Cool. All
Hey,
right.
thanks,
See you
y'all.
online. And in person. Let me stop recording.